Okay, so what we'll talk about now is this concept that goes under a few different names, but big O notation is a pretty popular one if you want to look it up on Google and look for other examples. So we're going to start off with a definition. We're going to say that a function, this is just purely mathematical, this is not computer science yet. A function f of n is, I'm going to call this big O, g of n, if there's a constant c and some initial value n, we'll call it n naught, such that f of n is less than or equal to the constant times g of n for all n greater than the particular n naught. Okay, so let's go over an example of this concept. Let's take the function f of n, which equals 4n squared plus 16n plus 2. And we'll ask ourselves, is f of n big O of n, let's say, to the fourth? Does this definition up here apply to this particular function? So what we would need to do is we would need to do this. We would need to take this function, 4n squared plus 16n plus 2, and say, is this less than some constant times n to the fourth? And what we can do is we could try to find out if there is such a constant. So let's try the constant. Let's look at this as our work area. Let's try the constant c equals 1. Okay, if c equals 1, we can get rid of this. Now, is this statement true? N to the fourth is greater than 4 times n squared plus 16n plus 2. Well, it looks like the answer is it's true for some n's and not other n's. So for example, if we let's say we had, let's do a chart. If n is 0, what happens? We get 0 plus 0 plus 2. We get 2 is less than 0. That's not true. Okay. When n is 1, what happens? We get 4 times 1 plus 16 plus 2. We get 22 is less than 1 times 1 times 1 times 1 is 1. That's not true. Let's try another n. When n is 2, we get 4 times 4 is 16, plus 16 times 2 is 32, plus 16 is 48, plus 2 is 50. We get 50 is less than 2 times 2 times 2 times 2, 2, 4, 8, 16. That's not true. Let's try another n, 3. When n is 3, we get what? 4 times 9 plus 16 times 4 plus 2. So what is that? 4 times 9 is 36. 16 times 4, 16 times 3 is 48 plus 36 is what? 48 plus 36 plus 2 is 86. 86 is less than 3 times 3 times 3 times 3, which would be 81. That's also not true. Looks like the next one should work. Right? 4. In the case of 4, what do we have? 4 times 16 plus 16 times 4 plus 2. 4 times 16 is 64 plus 6, that's 130 is less than 4 times 4 times 4 times 4. 4 times 4 is 16, 256. So that one works. So what we're saying is, I'm assuming I did this math right, what we're saying is that for a particular value of n equals 4, when n equals 4 or a greater number, this statement, this function is less than n to the 4th, becomes true. So it's for n equals 4 and all numbers greater than that. Let me double check this. 4 times 4, 16 times 16 is 256. And 4, yeah, okay. So for n is 4 or greater, and the constant, we could let the constant equal 1, this statement becomes true. So the answer to the question, is this function big O of n to the 4th, that would be a yes if we could come up with a constant, which we've come up with as 1, a constant and a particular value of n, where we say for that value of n and all values greater than it, this statement is true. If we can do that, then the answer to the question, is this function big O of n to the 4th, the answer is yes. And if we could never find a constant and a particular starting value of n from which that becomes true forever, then the answer would come out to be no. Okay. So, let's look at now another definition. There's another definition, and they use a Greek letter for this one, but big O I don't think is a Greek letter. But they use another Greek letter, omega. I think this is omega. This is a big omega. A function f of n is omega of g of n if there exists a constant c and a particular value n for which this is true. It's the other way around. And if that can be said for your particular function, then the function f of n is considered omega of g of n. So the definition we did before was big O of g of n. That's if the c times g of n is larger than the function from that point n onward. And then we have a different definition, omega, which says that if a constant times g of n is always less than your function, that's considered omega of g of n. So let's use that same example. Let's use the function f of x, f of n equals, what do we say, 4n squared plus 16n plus 2. Okay, now the question is f of n omega of, let's say, n squared? What we have to do is come up with a constant and a particular value of n for which from that point onward this statement would be true. This one is pretty straightforward because if you think about it, whatever value we put in for n, we're going to multiply it by 4 and then add more stuff to it. So we can take the constant, c equals 1, and then basically the particular value of n we could say equals 0. Because 4n squared plus 16n plus 2 is greater than cn squared. When does that happen? So if we choose c to be a 1, We take that away. And this pretty much happens right from the get-go because this plus 2 makes the value of this equals 2 when n is 0, and then everything after that, whatever we punch into n squared is going to get multiplied by 4 on this side, and it's going to get multiplied by 1 on this side. So it's pretty obvious to see that this question comes out to be yes. This question is answer yes. Okay. So that's the concept of the omega. Let's come up with an answer, a question where I know the answer is going to be no. Let's ask the question, is this function omega of n cubed? Now, in a short while, you'll be able to see right away this is not. But this is what we'd have to do. For the answer to come out to be yes, we would have to have this situation. 4n squared plus 16n plus 2 is greater than some constant times n cubed for all values of n beyond a particular value of n. The constant has to be a positive number, so we can't use a negative number. If it was negative, we could just put in a -1 and this would always come out true. Okay, so now the question is there a constant we can come up with that no matter how large n got, this term will always be less than this term? And the intuition is basically this. This term right here is the dominating term. When n gets to be very large, the fact that there's a constant of 16 in front of this will kind of drop out of the picture. This is going to be, 95% of the value of this side of the equation. The problem is this constant here, 4 right in front of it, will not overweigh whatever we put here. Whatever we pick as a constant here, even if we pick the lowest possible constant we can think of a 1, when n gets to be much larger than 4, this really turns into, this is really whatever constant we pick times n. This is really equal to constant times n squared. So the constant times the n will definitely be much larger than 4 times n squared. The constant times n squared will always be larger than 4, no matter how small we pick the constant to be. We just let the value of n run up to be greater than the reciprocal of it. Even if we were allowed to take fractions here, if we pick this to be 1/100, once n hits 100, this whole constant becomes a 1, and once n hits 400, this constant here is equal to 4, which is tied with this, and then once we let it go above 400, this term will run much larger than this term, and these are a lot smaller. The 16n plus 2 is a lot smaller than this when n gets to be very large. So hopefully you can convince yourself that this cannot happen. That whatever constant we pick, once n starts running up into large values, the constant times the n will dominate this function, and this statement will once again become false as the n's get bigger. So the answer to this question is f of n, which is this particular function, is it omega of n cubed? This is no. The answer to this question is no. Okay. Now there's a third definition we'd like to go over. And this is where we take the combination of these two. Okay, so we're going to say a function f of n is, we'll use another Greek letter, theta. Theta of g of n if two conditions are met. If two conditions are met. The first condition is f of, now I'll do it this way. Two conditions have to be met. Number one, if and only if, number one, f of n is big O of g of n, and number two, f of n is omega of g of n. If they're both true, then we use a new Greek letter, theta, and say that f of n is theta of g of n. Okay, so let's come up with an example where this is true. Let's use the example we just had before. F of n is equal to 4 n squared plus 16 n plus 2. And we're going to ask the question, is f of n theta of n squared? That's the question that's on the table. Okay. In order for this to be true, two things have to be true. In order for f of n to be theta of n squared, two things have to be true. Number one, it has to be big O of n squared, and also it has to be omega of n squared. So, I think that's a Q. Okay. So, how can we show that, first of all, f of n is, okay, so let's do the omega one first, since that's easier. F of n is omega of n squared. How would we show that? Okay, we choose the constant equals 1, and we choose n0 equals 0. So just as a reminder, the function 4n squared plus 16n plus 2 is greater than 1 times n squared. When is this true? Well, let's say, so that we had a constant here and we decided we're going to use the constant of 1. Okay? So when is this true? For what values of n? What positive values of n? Is this statement true? Well, it's true for every value of n, including when n is 0. So when n is 0 and greater, this statement is always true. Therefore, f of n is omega n squared. So that was generally the easy one. The one that's a little bit difficult to do, which usually requires doing a few runs of it and finding the correct value of n, is f of n big O of n squared. Now, just before we did, yes, it is big O of n to the 4th. Now we're trying n squared. This is a little different. So we need to have the situation where this is true. Right? Here's our question. And we need to have the situation where 4n squared plus 16n plus 2 is less than some constant times n. Okay. We have to come up with a constant with, n squared. We have to come up with a constant, it could be any constant as long as it's less than infinity. And then we could take, for a particular value of n, saying from this value onward, this statement is true. So it's allowed to be false for some low values of n. But once we get to a certain value of n, from that point on, this statement has to be true in order for this answer to come out to be yes. Okay, so right off the top of our heads, what are bad choices for the constant c? Bad choices would be any value of 4 or less. Here's why. Suppose we chose 4. I'm getting the 4 from here. Suppose we chose 4. When will this statement ever be true? For what positive values of n could this ever be true? And the answer is it could never be true. Because we have 4n squared here, and we have 4n squared here. But this is 4n squared plus more stuff, and this stuff's going to be positive. There's nothing negative here. So when would this side of the equation be less than this side of the equation? The answer is never, because we chose 4. Or if we chose 3 or 2 or 1, this will never happen. So we need to pick something so that when n squared becomes larger, this side will take over and be larger than this side. Okay, so let's not put a whole lot of thought into it. Let's make it 5. What happens now? Okay, so for different values of n, we have, let me do this. We'll say for values of n, and then here's the function, 4n squared plus 16n plus 2, and then here's 5n. It's 5n squared. Okay, so let's see what happens. When n is 0, what happens? This 2, and this is 0. We want what's on this side to be less than what's on this side. When n is 1, what happens? Oh, we did this before, so what is this? 4 plus 16 plus 2 is 22. And this is 5. So that's no good. We want this column to be greater than this column. When n is 2, what happens? 16 plus 32 is 48, plus 2 is 50. 5 times 2 squared is 5. 2 times 4, 2, 4, 8, 16. 16 times 5 is 80. Is this right? When n is 2, we have 4 times 2 plus 4 times 4 plus 16 times 2 plus 2. 16 plus 32 plus 2. 32 plus 2 equals 48, 50. Yeah, okay. So it looks like from this, if we choose a constant of 5 and n naught of 2, assuming I did the math right, from this point on, all other values of n, this is going to get bigger than this. So from 2 onward, this statement, f of n is big O of n squared, becomes true. And therefore the answer to this comes out to be yes. So this becomes yes. Yes. Okay. So the answer to the question is this function here, is it theta of n squared? The answer is yes. And the reason why the answer is yes is because both things are true. It is big O of n squared, and it is also omega of n squared. Okay. So now, why do we bother looking at this? What does this mean? In the world of mathematics, it doesn't mean a whole lot. But in the world of computer science, it could mean a few things. We've talked about programs that have a running time function. We use t to symbolize time. T of n equals, and let's say like the example we just had, 4n squared plus 16n plus 2. Let's say we had a computer program that had this as its running time, meaning if you ran the program, depending on how many inputs you had, where n is the number of inputs. You run the program, you look at your watch, and it's done. How long would it take? Now, how could a program have a running time like this? What does it look like is happening? It looks like, since there's an n squared term here, it looks like maybe the code, maybe the first part of your program does a for I equals 1 to n, for j equals 1 to n, and then it does something. So it's a nested loop. So that takes n squared times, and whatever it's doing in the loop maybe takes 4 seconds each time you go through the body of the loop. Then after that part of the program is done, a second part runs and goes through all your inputs. Let's say you have n inputs in an array. And each time it visits one node in the array, it does something that takes 16 seconds to do. So there's something very time consuming each time it visits the array. And then finally at the end, your program prints out, the answer is 12, or, somehow prints out, does one step at the end, which takes a constant amount of time, like 2 seconds, and then it's done. So let's say this was the equation for how much time your program ran. So obviously, as n gets bigger, it will take longer. So this would be a reflection of how much time your program takes based on the input size of n. So if we came out and made a statement that says the program, this function t of n, and let's say we drew a graph. If we said this program, and let's say this, I don't want to graph it too accurately, but it starts at 2 and then it starts shooting upward. It goes something like that. When we look at functions like n squared, when we had a constant of 1 times n squared, it would look something like this. And when we had the constant of 5n squared, right, so this was n squared, and 5n squared would look something like this, and this point where the crisscross was I think at 2. So this is a 5n squared. And what we're saying is that the program that you wrote, which has this as its running time, we can say that, so this brown line is the running time of your program. This line is this constant of 5 times n squared, and this is the constant of 1 times n squared. And we made the statement that your function t of n is theta of n squared. What did that mean again? So just as a little review. We can find a constant to put in front of here and then say for a particular value of n onward, this will be less than, this function will be less than that function. We also said that for a different constant, in this case we chose the constant of 5, for a different constant we can say that this function will always be less than a different constant times n squared from some point onward. So before the 2, your function was greater than this function. But that's okay, we're just saying from 2 onward, I can count on this function being less than this function, and I can count on this function being greater than this function forever. And what does that mean? What does the time function of your program is theta of n squared. What does that mean? That means as n gets very large, the dominating term of your time function is the term that has this in it, the n squared component. So let's look again at your time function. We basically said your time function, t of n, is equal to 4 times n squared plus 16 times n plus 2. This is how much time your program took to run. When n is like, let's do this, when n, here's n, and here's your time function. When n is 0, this takes 2 seconds to run. When n is 1, this takes 4 plus 16 plus 2. 4 plus 16 plus 2 equals 22. When n is 2, this is 4 times 2 times 2 is 16, plus 16 times 2 is 32, plus 2 equals 50, 50 seconds. When n is 3, we have what? 4 times 3 times 3. 4 times 9 is 36, plus 4 times 3, 16 times 3 is 48, plus 2 equals 70, or 86. When it becomes 4, 4 times 16 is 64, plus 16 times 4 is 64, plus 2 equals 120, 130. And so on. This could keep going on and on. What is the point I'm getting at? The first time, when n is 0, this is 100% of your program, the part of the program where it prints out the output. When n is 1, this term is probably almost 80% of your program. The second time through, this is 66% of your program. The third time through, this is maybe 60%. By the fourth time through, this is at 49%. And this has grown. This went from being approximately 20%. This now is 33%. This is now 40%. Now it's up close to 50%. And if it kept going, the percentage of this component will outgrow the percentage of all the other components. So now when we let n be ridiculously high, this is going to end up being this, whatever part of your program this is. Like we said, for example, this could be a nested for loop for I equals 1 to n, for j equals 1 to n. That section of your program is going to end up taking up 99%. If we let n go really large, it's going to end up taking 99.999% of your program is going to be spent on that step, and hardly any of it will be spent on this step. Even though this constant, this 16, is much larger than the 4, and let's say the 16 represents how much time you spend with each node you visit as you walk through the array, the 16 being larger than the 4 will mean pretty much nothing when n becomes very large. Doesn't matter what the ratio of these two constants are, when n becomes very large, this term will end up taking up 99.999% of the time your program takes to run. So how much time this takes doesn't really matter when n becomes very large. The statement that says my t of n function is theta n squared is basically making the statement that when n becomes very, very large, there's a part of the program that has its running time is n squared times some particular constant, which ends up becoming meaningless, but that ends up being the dominating term. That's the part of the program that when n gets very large is going to take up 99.999% of the time of the program. And this other stuff will become irrelevant. It becomes irrelevant when n becomes very large. If we said that the program runs big O of n squared, kind of like the example we made before, yes, this function is big O of n squared, but it's also big O of n cubed, and n cubed, n to the 4, n to the 5, any number greater than 2, you'll figure out this is true. This is just an upper bound that is so ridiculous high we don't want to talk about it. When we want to describe how good an algorithm is, we want to basically have the tightest bound we can. Out of all the possible big O's that there are, we want the lowest one that there is, the n squared one. And the way you signify that this is not only a bound, meaning this line will be larger than this line, So I can be guaranteed that my program will take less time than this. The way to say this is the tightest bound that there is to also show that it is omega, omega. And the way you say that something is big O and omega, you say it's theta. So you would think that when you're analyzing the running time of algorithms, you would think that the important thing would be to have it become theta. Because you're not only saying, I know my algorithm will run, the amount of time that my algorithm will run will be less than this function, and that you're not picking some ridiculously high exponent to make the point. You're picking the tightest, the smallest one you can, where you know that the running time will be less than this function. And the way to prove that, the way to make that statement is theta. But if you look at most of the literature, you would expect it to say, people would make statements like, oh, I came up with an algorithm to solve this problem, and my algorithm has a running time of theta n squared. But most of the literature will just say big O of n squared, and it's assumed that that's the best bound you can have. But theta would actually be a better way of writing it. Okay, so that's what this ends up meaning. When we go a little further on in the course, and we talk about the topic of sorting, we're going to talk about, we're going to come up with algorithms where we're going to say, oh, okay, the problem I have is I'm given an input of numbers, and my goal is to sort those numbers. And I've come up with an algorithm that can do it. And the running time of the algorithm, we'll come up with a running time for an algorithm, T of n, which is blah, 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 blah. And we want to be able to say, and this is theta of n log base something, base 2 of n. We might see statements like this. Okay, so we'll take a quick review of logarithms. What is a logarithm? A logarithm, I guess the best way to talk about logarithms is to say this. Suppose you were given a question like, what is 987,631 times 473? Well, you'd have to get out a calculator and punch it out because, this looks like it'll take a lot of time. But what if you were given a question like this? 1,000,000 times 1,000. Well, these numbers are bigger than these numbers, so you would figure this should be a harder question to answer. Yet you can answer this one right away. And what is the answer right away? The answer is 1 billion. And how are you able to do this one so fast and not this one, even though these numbers are smaller than these numbers? Why were you able to do this one so fast? And the reason is you used logarithms. You may not realize it, but you used logarithms. You said to yourself, what is this number? What is the log base 10 of this number? And this, of course, log base 10 of 1,000,000 equals 6. And then you said, what is the log base 10 of 1,000? Which is 3. And then you added 6 plus 3, and you got 9. And then you said, what is the inverse log base 10 of 9? And this equaled 1 billion. And that's how you solved this one. You used logs. You just didn't realize it. What you really probably did was you counted up how many zeros are here and how many zeros are here, and you added them together, and then wrote out the new number with that many zeros. Okay, Well, what is the concept of a log? A log says the log base 10, okay? The log base 10 of a number, let's say 1,000. You're asking the question, what is 10 to the watt equals 1,000? 10 times 10 times 10, how many times do you have to multiply 10 by itself to get 1,000? And the answer to that question, the answer is 3. 10 times 10 times 10. So that's what the log base 10 means. It means if I took a 10, how many times do I have to multiply 10 by itself? 10 times 10 times 10 to get 1,000. And that's 3 times. Okay. Let's try a different one. Let's try log base 2 of 8. What is this equal? 2 times 2, how many times do I have to multiply 2 against itself to eventually get to 8? 2 times 2 is 4, times 2 is 8. So the answer to this comes out to be 3. Okay, so that's what logs end up being. Logs are going to come into play when we start to look at algorithms that take an array of numbers, a set of numbers, and it divides them in half. Let's say we had a set of numbers that are from 0 to 7. We have 8 inputs. And let's say we had an algorithm that for some reason cut the array in half. After one pass, it cut the array in half. Now we're going from 0 to 3. Then took this array and cut this in half, and it went from 0 to 1, and then cut this in half and went from 0 to 0. How many times is this going to happen? Well, it's going to end up being 8 divided by 2 is 4, divided by 2 is 2. You keep dividing half until it goes away. Well, that's a lot like, this is the same concept in sports. When you have, 16 teams are in the playoffs, you have a round of playoffs, now you're down to 8, now you're down to another round of playoffs, you're down to 4, another round you're down to 2, and then you're done. How many rounds of playoffs are there? It ends up being log base 2 of whatever the original number was. Let's say it was 8. Log base 2 of 8 is 3. So for example, if you have like hockey and basketball is going on right now. If you have a playoff that has 16 teams, and they pair up 2 against each other, so you have 8 different games going on. And then only the winners get to survive. How many rounds of playoffs are there going to be? You take log base 2 of 16 and you would get 4. After 4 rounds of playoffs, we're done. Same thing's going to happen with sorting. We're going to take arrays and then we're going to have half its original value and a quarter, an eighth, and then eventually our algorithm will stop. And we want to know how much time did it take, how many runs of this were there. It ends up being log base whatever you decided to divide it by. If we divided it 1/4 each time, it would end up being log base 4. Log base 4 of 16, that means 4 times 4 is 16, that would be 2. Okay, so when we get to the topic of logs, and we get into this big O notation, we're going to notice that the log base anything of n is equal order log base any other n, a different base of n. This will always be true. And let's just go over an example. Suppose we have the case where case 1, where x and y equal each other. Well, then we could choose the constant of 1 and n naught equals 0. If they're both equal to each other, let's say is log base 2 order log base 2? Yes, right? We can just say, let's say f of n equals log base 2 of n. Is that order log base 2 of n? Well, yeah, we can put a constant of 1 in front of this, and then for every value of n, this is true. Log base 2 of n is less than or equal to log base 2 of n. Okay, so that's true. What about the case where y is greater than x? Suppose we have log base, for example, log base 2 of n is order log base 8 of n. Is that true? Well, in this case, we could take the, we could let the constant equal log base, so here's what the question ends up being. Is log base 2 of n equal to log base, is log base 2 of n order log base 8 of n, as an example. So can we do log base 2 of n is less than some constant times log base 8 of n. Now the log base 2 of n is going to be exponentially bigger than log base 8 of n, but if we then took as a constant, if we took the constant equal log base 2 of 8, which would be 3, then putting a constant of 3 in front of here, which a constant in front of a logarithm could also be put into its exponent, so that would be just a little something you might want to review from your math class. This would end up being true in all cases. And then in the third case, where x is less than y, that you could also pick c, the constant equals 1 and 0 equals 0. So, bottom line is this. You can take some time and review this to convince yourself that this is true, but if we ever produce an algorithm where the running time of the algorithm, the running time of the algorithm had a term in it that said log base anything, x of n. This function t of n is order log, and we have the flexibility to pick any base we want of n, if need be. So in other words, we don't have to worry about the base of the logarithm. We'll be fine no matter what the base is. So we'll be able to say, make statements, a vague statement like, my t of n, the algorithm I came up with to do some function that had a logarithm to it, like we were dividing the array in half and a quarter and an eighth. We could just say this is log, we don't even care what the base is. It has a running time of log n. We wouldn't have to worry about the bases.